So let's take a look now at functions of two variables and the level curves that we could get from these functions of two variables. So what is a function of two variables? It's basically a function where you have to give it two numbers in order to get a third number, which is the product of that function. A function of one variable, you give it one number, the x, it gives you back the second number, the y. That's the output. Well, now we have to give two things, so an x and a y, in order to get a third number, which is the z, as an output. It's basically a map from subsets of R2, the point space of the plane, to the real line. And we could write it as fxy. Sometimes you'll see it written this way, although you should note that we don't have to map the entire plane to the real line. We can just map a subset of the plane. Also, you sometimes see the identification of the range of the function with the z-axis, in much the same way that with functions of one variable you identified the y-axis with the output of the function. So now we have a z-axis which will give us the output. Also note that when you see a function written out as fxy, or z is equal to some other function, some function of x and y, then this is called the explicit representation. The function is given to you explicitly. It tells you precisely what you should do if you got an x and a y. So let's take a concrete example of a function of two variables. Here we have the function. We give it an x, we give it a y, and what does it do with those x's and y's? It subtracts them from, it squares each of them, and then subtracts them from 4 in square roots, okay? So here's the function written explicitly. It's the square root of 4 minus x squared minus y squared. And what is the domain of this function? Well, we're only dealing with real functions here, so no complex numbers. So we need that the argument that goes into the square root be positive. Otherwise, you're going to be dealing with imaginary numbers. So it can't be negative. So positive or 0. So we have this requirement that 4 minus x squared minus y squared should be greater than or equal to 0. Another way to write that is to just move the x squared and y squared to the other side, and we get this. And now try to think about what x squared plus y squared equal to 4 is. Well, x squared plus y squared equal to 4 is it's the circle of radius 2 that you see there. But that since x squared and y squared can sum to less than 4, then it also includes everything inside the circle of radius 2. So that's the set that you're seeing there in purple is the domain. And the domain gets mapped up to the real line along the z-axis, and the range is going to be from 0 to 2 along the z-axis. So here is the range, and here is the domain of our function of one variable, of two variables. And let's take just some two numbers to see what happens. So suppose x is minus 1 and y is 1. Well, wherever you see an x, you just plug in the minus 1 there. And wherever you see a y, you plug in 1, corresponding to the y value there. And so what does the function equal at the point x equals minus 1 and y equal to 1? It equals the square root of 2. So one way we could represent functions of two variables graphically is by looking at the graph of a function. Now, the graph of the function are basically, is composed of the points x, y, and for the z, you put in the value of fxy, okay? So if we were looking at the function that we have up here, then I would go to some particular value xy and map it up to the z that I would get from plugging in. For example, minus 1, 1, that's the point, say, down here. It gets mapped up to the square root of 2, okay? So the graph in red here are these red points. The red points that you see in this plot are the graph, okay? Just a set of points that respect uh, um, z being equal to the value of the function fxy, okay? So take, for example, what you're seeing up here. Down in this dark orange there, closer to brown, is the domain of some function. And for a particular x and y that we could vary, we could change the x and y, okay? Uh, those values get mapped up to some value fxy, okay? If you represent all of the points that x and y map up to, you will get what's called the graph, which is right there, okay? So in lighter orange there is the graph that you would get, which is composed basically of finding some x, y in the domain and then mapping it up along the z-axis, okay? So the dark brown there is the domain, and the range, which is giving you the graph when you take the range and identify it with the z-axis. That right there is the graph, the light orange. But we may also give a function implicitly. So up there I told you, when you write out f of xy and you actually give the expression for how you would get z given xy, that's called explicit, which you see right here as an example. You could also give an implicit representation of a function. And you could always do this. So implicit representation is basically where you give a relation between x, y, and z. This relation is represented by capital F. And you could set it to some constant, let's say 0. And through this relation, you would be the set of points that respect this relation would give you the graph of the function. All explicit representations may be expressed implicitly. Take, for example, so if we have, z is equal to f of xy, as we've seen before. Well, we could move this to the other side, and we would be left with this expression there. Moving fxy to the other side will imply that, z minus f is 0, okay? So why don't we then just define some new capital F function? It's going to be a function of all three variables there, x, y, and z, and set it equal to this, and set it equal to 0 in order to get the graph. That's possible, and we could do this for z minus, so up here we had this example of f of xy. If we have this relation here that you're seeing, so if we define capital F to be this, and we set it equal to 0, well, we're going to get the same set of points that we had for the graph, okay? So this might look like, just kind of a trivial move, but please do note that we could do other things if we just look at the expression z minus root of this, well, we could have squared the square root 4 minus x squared y squared, and then we would end up with this, okay? But that isn't exactly the function. So you could express more points that would fail the vertical line test using an implicit representation, okay? This is a sphere. That's a sphere of radius 2. And a sphere is not a function because a single point would have to get mapped to the top sphere and the bottom of the sphere. So you can actually get a larger set by using implicit representations that you wouldn't be able to with explicit representations. And sometimes some functions cannot be written out explicitly, okay? So that the only choice you have really is to represent them implicitly. I mean, we had problems like, say, sine of y plus e to the y. equals x, that relation can't be solved explicitly for y, and you're kind of stuck having to represent the function in an implicit way. So that's another advantage that implicit representations would have. So what you're seeing there is the ellipsoid. Looks, the function looks kind of similar to one of a sphere. It's just a bit different with the constants. And notice we could represent this explicitly with how we've done in a previous problem with x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. But notice that this would fail the vertical line test. I mean, you see that red line there, okay? You're mapping one xy point to z at the top of the ellipsoid and at the bottom of the ellipsoid. So in this case, an implicit representation of the ellipsoid could give you more points than taking two explicit representations, one for the top of the sphere and one for the bottom of the sphere or ellipsoid. On the other hand, the elliptic paraboloid there would pass the vertical line test, and its implicit representation doesn't really give us more information. We could express it, implicitly or explicitly.